Today we're diving into the fascinating and artistic side of coding, where creativity knows no bounds and programming languages are more about expression than practicality. Hi, I'm Daniel Sadiq, and here with me is my colleague Fadil Ubaidi. And in this tutorial, we'll explore the intriguing concepts of historic programming languages, or Esolangs for short. These languages are designed to push the boundaries of conventional programming, often serving as intellectual challenges, artistic endeavors, or humorous takes on traditional coding. Our table of contents for today's tutorial firstly is an overview on these languages, and then we'll go into the basics and advance of Piet programming language. First of all, Esolangs are programming languages created as a form of experimentation, humor, or art, rather than for practical use in software development. They often push the boundaries of what constitutes a programming language and explore new paradigms and programming techniques that challenge traditional ways of thinking about code. Here's an example of Hello World written in Bfund. And here's another example of Hello World written in Malbolge. And what you can see in common is that these languages are not readable. Today's focus is on one of the most visually captivating Esolang there is, Piet. Piet was created by David Morgan Marr in 2001 and named after Piet Mondrian, a Dutch painter known for his abstract geometric compositions. The primary purpose of Piet is to make the source code look like abstract art. This design serves as both a creative outlet and a challenge for programmers who enjoy working with visual logic. Compiler moves in a two-dimensional grid, and the instructions in Piet are determined by the change of lightness and color between pixels. Here's an example of a Piet program where the output is "We dream and accomplish," the main motto of KFUPM.
So after we learned about Piet and esoteric languages, now we will dive into the basics of Piet. So as we said, the instructions in Piet depends on the colors, and there is two variables for the instructions that determine the instruction, which is the hue cycle and the lightness cycle. So let's see the tables below. Let's take an instruction, for example, subtract. In subtract, if the hue change is 1 and the lightness change is 1, that means the instruction is subtract. So if we, for example, moved from red to dark yellow, as we can see, the change in the hue is 1 and the change in the lightness is 1. So this gives us a subtract. And subtract, we will see later on, it pops the two upper value of the stack and subtract them and push them to the stack. We'll see later. Here is a terminology defined by the person who wrote the language, which are codels. Basically, codels are pixels, but they are enlarged. So for us, we can see, as you can see here, if we take the pink one, it is only 4 pixels. If it is really 4 pixels, we can't see it. But the compiler enlarges these pixels for us to be able to see it. And these pixels, we call it codels. A color blocks. Basically, a color block is a contiguous pixels or codels of the same color. As you can see here, this yellow block is a color block, even if there is green between them or blue in the border, they are still the same in the same block. But if we have a yellow in the kernel, like here, it will be not in this block, it will be in another block. So this is the concept of color blocks and codals. Stack, basically the stack is a data structure, and Piet uses a stack for storage of all data values, and the data values actually are only integers, and later they will be converted either to Unicode or they will be treated as integers. But what is different in Piet is that the stack has a maximum can have a maximum size. So if we exceed this size, it will be an error. Here is an example of the stack. If you don't know the stack, when we pop from the stack, we pop only from the top, and when we push to the stack, we push to the top. So it is the stack.
Okay, and now for the program execution. When a program executes, we have two pointers. One is the direction pointer, and it has values ranging from right, down, left, up, in this order, clockwise. And the other pointer is the codal chooser, which has left, right. And for short, we use DP and CC. So initially, we have our grid, and the interpreter starts at the top left corner. Initially, direction pointer is right and codal chooser is left. Okay, so what do these pointers signify? Okay, let's say, for example, that we have this code block. After the interpreter moves, it will go to the right, the direction pointer. So it will go to the furthest codal on the right. And if we have these two codals to choose from, it will choose the left one. You can think of it as if the codal is moving forward, which codal is it gonna choose, the left one or the right one? So you have to put yourself in the place of the interpreter. And if that's too confusing, there's this handy table which can tell you which codal will be chosen. So in this example that we had, the DP was right, the CC was left, so the uppermost codal will be chosen. And for the syntax, we have three main things. We have numbers, white blocks, black blocks, and edges. Okay. Numbers in Piet represent a block of colors, and they are the number of non-black and white pixels. For example, if we have this program, this block, code block, represents 12, and this purple one represents 9, the red one represents 4, and the blue one represents 2. Black and white pixels or codals don't represent any numbers. And this means that we can only represent integers. We don't have any other data types in Piet. Black blocks and edges. When the Piet interpreter attempts to move into a black block or off an edge, three main things happen. First of all, it will stop and the CC pointer will be toggled. So either it will change from left to right or right to left. It will then attempt to move again. If it still fails, then the DP is moved clockwise. So if the direction pointer was initially right, it will go to down. And and these three steps will cycle. If after 8 attempts the interpreter cannot leave its current color block, then the program will terminate. For example, we can see the interpreter here in the top left corner with DP initially right and codal chooser left. It will continue forward until it hits the first black edge. The direction pointer is still right and the codal chooser is still left. It will then toggle the codal chooser. It will become right. It still couldn't move, so it will toggle the direction pointer. It will go down, and we can see it will end up in this codal. the bottom left caudal. White blocks are very simple. They are basically no operations. The interpreter will basically glide through them and move straight forward until the next color.
Look through them. So first command is push. Basically, it's push the value of the color block, just exit to the stack, which means if you have a block, if you have, for example, a yellow block of 44 cuddles, when we push it to the stack, 44 will be pushed because the count of the cuddles in this block is 44. And the same for Bob. No, for Bob, we bob the top of the stack and discard it. For add, we bob the two values in the stack and add them and push them again to the stack. Same way for subtract, multiply, and divide, but the operation is different. Not is interesting because later on we'll see when we combine it with another instruction, we can define a loop. So basically not replaces the top of the value of the stack with 0 if it is non-zero and 1 if it is 0. It's like the opposite of not that we know. Mod, so like the previous ones, like add and subtract and multiply and divide, it mobs the two values of the stack, calculate the second top value modulo the top value, and pushes the result back to the stack. Greater, it pops the two values of the stack and push one to the stack if the second top value is greater than the top value, and pushes 0 if it is not. Pointer, it pops the top value and change the direction of the pointer based many times of the value. Switch pops the top value of the stack and tackles the CC. We will learn about the CC later. That many times. Duplicate, basically it duplicates the top value of the stack. Here another instructions, role. I will skip the definition of role here because we will see it in detail later on. N basically receives an input, either a number or a character, and out we will print out an input, the top of the stack. So for the interpreter for Piet, we will use this website, which is a very good website, and it helps you very much. Now we will take an example, which is a hello world example. I will not write it because it will take very long, but I will debug it with you in this website. So let's go to the website. As you can see, I opened two windows for the website. One to see the instructions and another to debug. So let's understand together. As you can see, we will start from the top left corner here, and the color is chosen to be red. Does not matter, you can choose any color. So I chose the red one, and from the red, as you can see, the pointer will move like this to the right. Here it will reach this color. As you can see, from this color to this color is push. So if you start step, it is 72, which means the number of cuddles, red cuddles in this block, which is 72. Basically 72, as you can see in the ASCII table, it is H. So we are pushing H to the stack. Here we will move to this cuddle and we will push H to the stack. So the color here, if you choose it, as you can see, we are in this color, and we want to output H. Here is out C. So that's why we put this color after this color. Now we have a number of pink or pink color, which is 101. And if we checked the ASCII table, 101 means E, small e. And now I will test you. What should we do? As you can see, what should we do? Yeah, we should push this 101 to the stack by putting this color. As you can see, here we pushed 101 to the stack. And the other instruction we need is output C. Here, we choose output C and we output C. If you step, it will be output 101, which is E. And the same way will goes, but here is another concept. As you can see, the pointer is moving to the right, but it collides with our border. So, as we explained later, the pointer will change its direction, but before it changes its direction, the CC will be toggled. So as you can see, the CC toggled, and it goes to the right with respect to the arrow, or down with respect to us. Because if initially it was up, but now it is down. As you can see, CC is bottom. But still, there is a collision. If we step, there is a collision. So the second collision, the pointer will move clockwise. So it was right, it will be down. And we'll continue. Now, step again. The count of number of cuddles here is 108. And we pushed it to the stack. So initially we were in this color, and we use this color to push 108 to the stack. And from this color, we want to output C. And that's why, no, before outputting C, we duplicated C. We duplicated 108. So to duplicate, we use this color. We duplicated, as you can see, and pushed it to the stack. Now, again, let's see what happened. We duplicated A again. Then we outputted C. As you can see, here is the color, and it is output C. We outputted C, which is L. Now he will output again, out C. We are in this color. This is out C. As you can see, L. So this is the concept. We will repeat these concepts for the other letters. But what matters here, if we go, as you can see, the pointer will reach. Yeah, the pointer reached here. So now, as you can see, we printed hello world, but I think he wants to print the bank, so we printed the bank. But what should we do now? How can we stop the program? We finished. So if we step again, you can see the pointer still colliding with black color. Step again, the pointer colliding with black color. Step again, we collide until it stopped. So basically, to terminate the program, you need to collide 8 times in sequence. And to do that, you can use this shape or any other shape based on your imaginary. And that's the debugging hello world.
And now that we finished the most basic example, hello world, we can now move on to more complex and advanced techniques in Piet. First of all, the not command and the pointer command. When a not command is followed by a pointer command, the program effectively uses the result of a logical decision to influence the flow of execution. So what I mean by that, is the not is a way of checking a condition, a logical decision, and the pointer is used to change the DP pointer, which basically changes the way where the interpreter will move. So we can basically make a map and based on this concept choose the flow of execution. Okay, so here we have this loop in Python. While I is not equal to 0, do an operation else decrement. So the equivalent in Piet commands is, first we have to duplicate, since the not command will consume the top of the stack. And since 4 is a non-zero number, then the top of the stack will become 0. After that, we can use the pointer command that will change the flow of the DP based on the top value. And since it's 0, it will remain unchanged. And it will continue so until the top of the stack changes to 0, then it can continue into another flow of execution.
Before, we will explain role in detail, and here is the explanation. So we have this schedule or this table. We have the depth and the stack. So basically the depth is like the index. It is not an index, but you can think of it like that. Let me remove the toolbar. Yes. Now we have these these are the elements of the stack, and the top two values are 2 and 3. The top value is 2 and the second top value is 3. Basically, role will take the top two value, okay, and the top value will be the number of roles. The second top value will be the depth of the role. So we can see here stack before rolling is 50, 40, 30, 20, 10 because we popped this. Now the stack after the first roll will be 50, 10, 40, 30, 20. Why? 10 is the top of the stack. We'll move it to depth 3. So depth 3 is here, and we moved 10 here. The other values, we moved them above 10, or yes, above 10. So this is the stack after first roll. After the second roll, the top of the stack here is 20. But after the second roll, we will move 20 to the third depth of 3. So 20 becomes here, and 10 becomes after it, and 40, 30, and 50 will not change. If we said instead of 3, 4 here, 10 will be here, then 50, 40, 30, 20, and so on. So this is role. So after we learned about role and the other instructions, we will apply them in binary to decimal program. I will explain it at the website and debug it. So as you can see here, this is the pseudocode for binary to decimal. We need variables, which is a container. Here, as you can see, we need a container to have the summation of these values, and another container for the base. Okay, so how can we apply it in Piet? Let's see. Let's start. And I started with this color, which is pink. Now, from pink color, I chose red, which is push. So we pushed what? We pushed 1 because there is only one cuddle for the pink color. After that, I chose this color, which duplicates the top value of the stack. As you can see, if we step, the stack will be 1, 1. Then here is a dark magenta. You can guess what is the number, right? Which is what is the operation, which is subtraction. And we step, basically subtraction will take the top two values of the stack and pushes the result, which is 0. Now, this is the decimal value here. This is the corresponding value. Okay. Now we need another one for the base. So let's go and debug again. Let's see what's the next step. We have this from the magenta to this step. We pushed one. Sorry, from this to, yeah, from this to this. We pushed one. And from this color, we duplicated one. And this is our eye. We duplicated our eye, or not eye. What's they calling them? They call it base. So we duplicated the base in the stack. Now, from this to the dark dark yellow, we will take an input. So let's give it an input, or let's reset and give the input from the beginning. It will not take it when we execute the program. So let's, for example, take 1111, which is 15. No, it will take so long. So let's take it 11, which is 3. And we stopped here. Now the operation was n, and we take the input is 11. And from this dark yellow, we move to here, which is duplicate. So we duplicated the inputs, which is 1111. Now from this, we will use NOT. And basically NOT checks if the top value of the stack is not 0, it will push 0. As you can see, it pushes 0. The other instruction is the direction pointer, and direction pointer will change the direction of the pointer depending on the top value of the stack. So it is 0, and the direction pointer will not change. If it is 1, it will change once. If it is 2, it will change twice in the direction of clockwise. Now let's step again. From this color to the green, which is duplicate. So we'll duplicate 1. And the reason we duplicating these numbers, as you can see, because later on we will multiply them or subtract them. So we lose them. We don't want to lose them. We duplicate them from the beginning. This is the reason. So we duplicated 1. And now we will push, as you can see here, is this this group of this block of colors is 10 cuddles. So we'll push 10. As you can see here, push. So step, push 10. Why is that? Because we need 10 to have the modulo and to divide by 10. So we pushed it. Now we take the modulo. So we'll take the modulo of the top 2 values and push them to the stack, to push the result to the stack. As you can see, we moved from light green to blue, and it is modulo. And of course, 11 modulo 10 is 1. Now the stack pointer will hit and will change its before it changes direction, it will change the cuddle. So it will move down. As you can see, the cuddle is top. It will change it to down. Toggle it to down. Okay. Toggle it to the left, then toggle it to the right. Then the direction pointer becomes down. Okay. Now, from this blue to dark blue, which is push. So this blue is 3, so we'll push 3. And you'll know why. Here, another push 1. Okay. As you can see, from this light magenta or light blue to this green, the instruction is roll. So we roll to depth 3. We roll the top of the stack to depth 3, which means we roll this one, 1, 2, 3 here. It will be here. So let's go. Oh, I run this by mistake. Yeah, we rolled the stack basically. Now we are in this color. We will push again. As you can see, here is 10 cuddles in the block of green. When we change to dark clear, it will be push. So step, we push 10. Now before we took the modulo, now we will take the division. As you can see, from dark green to dark blue, it is a division, and we will divide 11 by 10. The result is 1. Again, the pointer will change because it was CC left. Now it will hit, and the direction pointer became left. As we know, the direction pointer moves clockwise. Now we are in dark blue, and we move to light blue, which is push. So let's step. We pushed 5, which is the number of cuddles in here. And now again push. We pushed 1. And as you can imagine, we will roll. So from here we will roll. So let's see what we are rolling. We are rolling this one to be the first one. Roll. We rolled it to be the first one. Why is that? Because we need to multiply the top 2 values, which is the base times the least significant bit, or the number divided by 10. So we are in green. We'll go here and we will push. We'll push 2, and we will push. We will multiply. Sorry. Yes. Now we are calculating the second base, which is 2i. Here, he's multiplying the base by 2. We will do the same thing here. We did it actually. Now, from here, as you can see, it is dark yellow. And the reason is that we want to duplicate 2i. Same as the reason we duplicated I, because we need it to be multiplied by a value, and we lose this value. So we need a duplicate of it. Now we will push, as you can see, here is a 5, dark yellow. We'll push them, or 6, sorry. And here is 2. We will push them. So basically, we will roll. We pushed 6, we pushed 2, and the next instruction is from here to here, which is roll. As you can see, the direction of the pointer will change, and it will change to this block, and we will roll. But why did we roll? We rolled because we need to multiply 1 by 1, which is the previous base, not the current base. The current base is 2, but the previous base was 1, which is 2 to the power 0. We multiply it by 1 divided by 10, which is 1. Now we multiply, as you can see. Or sorry, we are adding before multiplying, right? Let's check. No, we are multiplying. So yes. So multiply 1 by 1 and push 1. Now from this, we are going to the yellow. Basically, we said that the 0 is our decimal value here. So we will sum it with the result of the multiplication. As you can see, the summation is yellow. So let's step again. We summed it. And we will move from the yellow to the dark yellow to push how much? To push, let's see, we pushed 4, and then we pushed 1 to roll the stack. and to have this structure, which is here is the same as the beginning. Here is the summation, here is the I, and here is the number, which is n divided by 10, same as we did previously, to have the same structure. And the here the white is no operation, and the same would repeat again if we moved. Okay, we moved here. As you can see, the result here is 3. The next base is 4, but we will not execute it. Why? Because the top of the stack is 0. And when we go to not, it will change 0 to 1. Okay. Now the direction pointer will change 1 time. As you can see, it's changed down. Now from this, we will pop the values until we have 3 to be the top of the value. So we will pop, can see pop, pop, pop. And now from this blue to this, we will output C, out C, as you can see. So output C. And to terminate the program, we need to kind of make the pointer collide with the borders 8 times. As you can see, it collides once, twice, third, fourth, fifth, sixth, seventh, eighth. No, still 8th, and the program will stop. And this is binary to decimal. I hope it's clear.
There are 2 more examples which will be in the description, which you can which you can go through and follow and debug and find its output.
We learned about Piet. We learned also the concept of esoteric languages. We debugged some programs, and we learned about the direction pointer and the stack. So here is the recap. These tables are very useful to recap the concept that we discussed. These are all the instructions, and these are the colors that accepted in Piet. And here is the table that can help you to know which cuddle will be chosen. The resources are listed here. So here is the quiz. The answer will be given in the description later on. So I will go through the quizzes just to show you what they look like. And you can find the answers in the description. Thank you for listening. And if you have any question, this is my email and my number.